Hello everyone. Welcome to the session on achieving operational excellence for big data pipelines. I'm Shantanu Shirvastarva. I currently work as a software engineer at Zeotap. I've been in the company for around 3.5 years, working as a part of data engineering team, building the core Zeocode platform, doing all the egress and ingress pipeline management. And in this session, we'll try to deep dive into the challenges which are actually faced by companies working with the big data pipelines, and we'll see how to reduce the operational footprint of these pipelines and basically reduce the engineering intervention for maintenance. So I'll start with a bit of introduction about Zeotap. So Zeotap is a customer intelligence platform which essentially onboards first-party and third-party data sets. And we actually try to blend in these two data sets, and which enables brands to better understand their customers. The intelligence bit actually comes from the machine learning models and recommendations that we have built in on top of these data sets, and which basically enable us to generate some kind of actionable insights. Zeotap primarily operates across multiple geographies, and EU being one of them. So, in terms of the data governance, so EU is pretty strict on the GDPR compliance side of things. So that is why we have actually incorporated privacy as a first-class citizens for all our data pipelines. We have onboarded over 150 data partners into Zeocore as on date, and these data partners actually serve around 10 different products in Zeotap, which cater to different ad tech and martech offerings. So talking about the current scale of data pipelines at Zeotap, so as I mentioned, we have around 150 plus data partners, which range across 10 different products. So these for actually running pipelines for these 10 products, we actually leverage around 20 odd data prop clusters in GCP. Now, most of the compute, actually about 90% of this compute is based out of PVMs, or the preemptible instances, which GCP provides. So in terms of cost, PVMs are definitely cheaper than the on-demand instances, but again, there's a caveat that these instances can be actually taken up by the cloud providers once the demand for the on-demand instances surge. So again, these type of interruptions could actually lead to some kind of transient failures, and probably just a return operation on your jobs would actually solve this particular issue. So we currently run around 400 different workflows, which actually process around 2 terabytes worth of data on a daily basis. So talking about the older implementation that we had at Zeotap, so we had around 20 different clusters back 1 year, and these clusters were actually equipped with Uzi servers, Livy servers, as well as a Hue console. So for people who are not aware of these tools, I'll just give a brief about each one of them. So Uzi is essentially a workflow scheduler for Hadoop pipelines, which basically exposes an XML-based DSL for chaining actions and scheduling your jobs. So it also provides some kind of coordinator, which is actually a cadence-based thing for scheduling your jobs. We have a Livy server, which is actually a standalone Spark job server, which provides a REST interface for launching standalone Spark jobs. And Hue is basically a web interface, which is basically giving UI for Uzi or say Yarn jobs. So basically, to onboard any new job, or say to track any of the jobs which are actually running in the system, the developers had to actually interact with 20 different clusters and individually figure out, say, a particular coordinator in Uzi and check the status of that particular coordinator. Now, for a team of around 8 to 10 developers, the task of actually, maintaining or say tracking around 400 different pipelines is a very challenging task with this particular setup. As you can see, the operations or the operational effort required for sustaining this particular these kind of pipelines is very huge. And again, we have some kind of challenges as well with this particular implementations. So one of the challenges is with respect to the cascading failures. So, for example, a data partner ingestion was set up on a particular date, and say 10 days later, the data partner had actually changed the input schema for that particular date onwards, from that particular date onwards. So what will happen in that case is basically the job will start failing from that particular date, and it will keep failing, which would lead down to cascading failures. Now, if the developers are not, very alerted or proactive about the email failures, which is something what we had actually relied on earlier with this particular implementation. So this would actually mean that the job would be actually failing for say 10 days, 15 days before actually some kind of product escalation has been raised, and then the developer would actually go to the respective cluster and manually check the dates for which the job needs to be rerun, and will probably hit the rerun button over there and would again keep on monitoring things and just see if everything is working fine or not. So again, as you can see, the operational effort required to maintain such a pipeline is very huge from a developer's perspective. Coming to the dependency management side of things, so in this example, you can see a particular workflow. The transform flow is actually dependent on three different ingestions, which is DP1, DP2, and DP3. And we have a merge flow, which is basically consuming the output of this transform flow and also taking into account the last output of the merge flow and doing some kind of aggregation on top of that and piping this particular output to 10 different consumers. So what happens if one of the upstream flows, say DP1 ingestion, fails? Let's see. So DP1 ingestion failure would actually mean that the transform flow would also fail because the parent dataset has not been created in the deep storage, and which would in turn mean that the merge flow would fail, and which would lead to failures for n different consumers. So basically, the master dataset generation job failure would actually trickle down to all of the downstream consumers, and which would basically cause some kind of a failure avalanche. And in this snapshot of email, you can see for a particular master job generation failure, we have around 10 different failures for the downstream consumers. And you can imagine rerunning all of these jobs is again a very operationally heavy task, because you can see that these jobs could be probably spawned across say 3 different clusters, and just figuring out the appropriate UZI coordinators from these 3 clusters, and then just checking what all dates have failed and trying to rerun all of these jobs is again a very I would say not a very smart way of handling things. So we have looked at cascading failures, we have looked at problem of workflow dependencies, we have seen what is the involvement for rerunning a particular workflow in case of any failures. We'll talk about multi-workflow tracking as well, so which is basically something which we actually faced a lot of times in the previous implementation. So we have different clusters. Now each cluster is equipped with a different UZI server or Livy server, and say an Airflow server as well. So now your jobs are actually spawned across these 3 different stacks. One of them is UZI, one of them is Livy, and the third one is Airflow. So what happens if you want to have some kind of a consolidated view about a workflow tracking? So you cannot have that because everything has its own interface. So UZI would have a separate UI for tracking the jobs, Livy would have a separate UI for tracking these jobs, and actually Airflow also has a separate UI for tracking its job. So again, you don't have a unified interface for tracking all of these jobs which are actually running on a daily basis, and this kind of view actually raises a lot of important questions. So questions like what is the current status of a DP ingestion, right? Or say when was a particular DP first ingested in the system, or are we meeting SLAs with are we meeting the ingestion SLAs with DP4? All of these questions cannot be answered without any kind of developer intervention, because first of all you'll have to figure out exactly on what resource the DP1 job was supposed to run. And then once you figure out that, you'll just have to log into a particular cluster or say a UI, and then you will have to check the individual coordinator status and then revert back to the product or TAM team. So again, as you can see, for every of the system visibility aspect, a developer intervention is required. And again, from an operational standpoint, this is something which is not scalable if, say, the workflows keep on increasing at a rapid pace. So with increasing scale, we realized that more and more developers were getting involved in maintaining and managing all the pipelines. So we decided on reducing the operational footprint of the complete system, and we tried to implement some kind of state management with some kind of automation inbuilt, and that is where Kingpin came into existence. So by definition, Kingpin is a person or a thing that is essential to the success of an organization or operation. So that is what Kingpin has been to Zeotap so far in the past 1 year, and we'll see how. So in terms of architecture, so Kingpin has a front-end service which is actually talking to the end user with respect to all the workflow registration or say status requests. We have a backend service which is actually talking to a metadata service which is storing all the job configurations, for example, cluster mapping or say job engine mapping, whether this job is supposed to run on Oozie or say Airflow. And we have a workflow DB which is tracking the status for all the coordinators in a Postgres instance. So again, we have integrated Kingpin backend service with an active MQ broker, which is actually in a queue which is based on GMS specifications. So basically, for any of the launch job event or a state change event, we actually drop an event to the queue, and we have subscribers on top of this particular queue. So we have a queue, we have a subscriber for job launch service, which would be actually processing the job launch events, and which would internally be talking to Oozie, Libby, and Airflow through the client implementations or say REST APIs, depending on the type of the job engine. We have a notification service which is actually responsible for propagating the notifications back to the desired notifications group. So in case of any job failure or suspensions, we'll have the relevant stakeholders get notified by sending an event to the active MQ broker, and the subscriber from the notification service would actually be delegating the emails to the uh, desired notification group. So we also have an inbuilt metrics collector, which would actually be, reading all the metrics from deep storage for all of these jobs which have been scheduled via Oozie, Airflow, or Livy. And it would basically collect all of these metrics and dump it back to the workflow DB so that we can have a correlation between the job launches and the metrics that would give us some idea on the job runtimes as well. So we have actually incorporated some BI tools on top of this particular workflow DB. So we have integrated it with Redash and Superset, which is something that is going to definitely improve the visibility of a particular system. So, and in some time we'll see how. So talking about the dependency management, so we had earlier seen how dependency management was a challenge in the previous pipeline. So, in terms of dependency management, let's take an example of a simple flow, a merge processor which is actually dependent on two DP ingestions. So we have DP1 and DP2 ingestions, and what Kingpin provides you is with a easy to use JSON-based DSL to express this kind of dependencies. A DP1 ingestion has been encapsulated as a node, and DP2 ingestion also has been encapsulated as one of the nodes, and these two have been connected by an AND operator in this particular JSON. So this particular JSON is now converted into a tree-based structure, and you can see that we have a non-leaf node for an AND operation, and we have a leaf node for DP1, and we also have a leaf node for DP2. So we have support for workflow level and data level dependencies as of now. So workflow level dependencies would basically mean that we'll just check if that particular workflow is successful or not for a given run date. Data level dependencies would come into picture when, for example, some of your jobs would actually rely on some third-party metadata which is actually stored in some deep storage or say HDFS. So in that case, what you will do is have some kind of a check that trigger this job only when this metadata is actually present. So for that, the data level dependencies can be used. And evaluation of this dependency tree is actually just a tree traversal. So if this is true, then this is also true. If this is true, this is false, then the whole dependency tree is false. So in terms of an extensible interface, we can see that a dependency node is an interface which has two different implementations. One is a leaf dependency node and the other one is a non-leaf dependency node. So non-leaf basically encapsulates all the relational operations between your leaf nodes. And in terms of leaf nodes, we have two implementations for workflow dependency and data dependency. In terms of extensibility, we can also have some kind of a resource level dependency down the line, which would basically check for some kind of external services. So for example, if your job is talking to an external API or say some database, so we can actually do a check if that particular endpoint is up or not before actually triggering the job. So that is something which can be easily extended into the parent system. So in terms of the execution strategy, so this is a complete flow for a Kingpin workflow. So we can see that there is a workflow registration request. So any new workflow is actually onboarded through this particular service, and we create an entry in the workflow registry table with the set of dependencies that it is supposed to have. Again, we have some kind of a frequency-based mechanism for schedule-based jobs. We also have some kind of trigger-based jobs. So not all jobs are actually, schedule based. So for example, if I have some kind of an ingestion flow, now I need to run some kind of a reporting flow on top of it. So basically what will happen is that once your ingestion flow is complete, you will have a trigger attached to that ingestion flow, which would actually will be responsible for triggering the reporting flow. So that is how trigger jobs are modeled in our system. So for basically the periodic jobs or the schedule based jobs, we have a periodic scheduler, which is actually iterating over all of the workflow registry entries, and which is talking to the flow manager for launching the jobs. The flow manager will internally validate the dependencies. So it will first fetch the dependencies from the workflow registry table, and it will try to check if it, in case of workflow dependence, if in case of workflow level dependencies, my entries are actually present with a successful state in the workflow status table, or in case of say data level dependencies, do the corresponding files exist in the storage layer or not. So in case the dependencies are not present or are marked as failed, so we'll just fail this complete job altogether, and will not launch the flow, which is basically going to save a lot of resources. And in case the dependencies are satisfied, we'll just drop an event to the job launch service, and which would be responsible for triggering the external flow, be it a UZ flow or say an airflow workflow or say a Livy job. And once we have a response from the job launch service, we'll just update the status accordingly in the workflow status table. And in case of periodic scheduler, we also have a catch-up mechanism where, based on the frequency, you can actually figure out if based on the current date and frequency, do multiple instances of this workflow need to be launched so that it is caught up till latest date or not. So all of that is taken into account by the periodic scheduler itself. So it would trigger the flows if it is lagging. If it is not, then it will just leave it as is. So, and in case of trigger request, we directly talk to Kingpin via the API endpoint, and there is no periodic scheduler involvement over such requests. So it is basically an on-demand thing. So in terms of failure handling and notification, so we have something for automatically retrying all the failed workflows. So we have a mechanism of actually having configurable retries at workflow level. So what that means is basically you can specify the number of times a particular job needs to be retried before actually being marked as suspended or say in an archived state. We also have some kind of a retry granularity. So by retry granularity, what I mean that we can have a full retry for a particular flow, we can have a partial retry for a particular flow. So a partial retry comes into picture when you have a very long running jobs or resource intensive jobs in your system. So for example, if I have one UZ workflow which is actually made up of say 4 actions, and each action takes like almost 2 hours to complete, so that would mean an 8-hour end-to-end runtime. So, and suppose in case of that flow's execution, the job fails at say 3rd action, so you have already spent 4 hours in successful computation. But the next, if you kind of incorporate a full retry for this particular job, you'll see that you are actually kind of wasting those 4 hours worth of compute, because you already have data available for those particular actions. So that is where the partial retry mechanism comes into picture, and definitely for long running jobs, it is something that is desirable. All of these state change events, basically, which is basically say a successful registry event, or say a suspend registry event, are actually broadcasted to the notification service so that the appropriate stakeholders are notified about the same. So a typical flow for a retry mechanism would look something like: you will have a workflow registry, and for each registry you will just see what is the candidate execution date, and you'll check if the end time has exceeded or not, because for every schedule based registry you need to have a start time and end time as well. So you'll just check if the end time has exceeded or not. So if it has, then you'll just mark the registry as successful. You'll just broadcast the event to the notification service and update the status. In case the end time has not been exceeded, that means that we can launch a candidate workflow for that particular run date, and we'll just first validate if the threshold for the job execution has been exceeded or not. So we'll just get all the failed actions from the workflow status tables, and we'll just see if the job threshold has exceeded. If it has not, then we'll just launch the flow. If it has, then we'll just suspend the registry and notify the watchers accordingly. So now coming to the visibility side of things, we had already seen how in case of some requirement from a product or TAM team with respect to any ingestion state, a developer intervention was something that was required for every question. So in this thing, in this basically Kingpin's implementation, what we had tried is kind of decoupled the visibility aspect altogether. So we have exposed workflow DB using some BI tools like Redash and Superset, so that uh, individual products can have individual set of dashboards which would be relevant to through the product requirements. So that is efficiently helping us to track the state of a particular ingestion. For example, if a product team asks what is the current state of this particular ingestion, I can just see what is the current state, or what was the first successful run rate, or what was the last successful run rate, till what date the ingestion has been caught up. All of that can be just answered without any kind of developer intervention through this particular widget itself. In terms of SLA tracking as well, we have some kind of widgets which would actually help you to get the last flow execution time, or say an average execution time for last 10 flows, and which would basically keep your SLAs in check. And you can also create alerts on top of these SLAs, and that would actually notify the relevant stakeholders with respect to some pipelines having stricter or harsher SLAs. So, as already mentioned, decoupling the visibility aspect from the core aspect would mean that you can have some kind of custom reporting requirements based on the product asks. So, for this particular thing, we can see that we have also integrated the workflow registries with relevant Jira tickets for suspended entries. So if a workflow is suspended, the developer don't need to scout for the errors or say the logs. Everything would be encapsulated in this particular Jira if some developer had actually worked on it earlier. In case of job logs as well, you don't have to log into the individual cluster and figure out what was the instance which was failed, and then just go and see what are the logs corresponding to those particular failed entries. So we have tried to put in the notion of job URLs as well with this particular dashboard, and which would definitely drastically reduce the on-call operations. So in terms of visibility and metrics integration, so we have kind of integrated all of these Spark jobs with Kubel Sparklens, which is an open source tool which would basically generate metrics based on your Spark jobs performance. So we have actually tweaked in a bit to actually dump these metrics into some kind of a deep storage, and we have set up cloud events functions on top of these deep storage buckets to actually process these metrics and put it into a consumable format in the Kingpin's database. And once you integrate it with Superset, we actually get a holistic view of your job's performance. So you can see what was the executive memory that was configured, what was the peak memory that was used by this particular job, what was the runtime that you have actually spent for this particular job. Sparklens also supports some kind of modeling for prediction of the ideal runtime or critical path time, or calculating app wastage or executor wastage. So all of these metrics would definitely help the developers with tuning these jobs further from a cost-effective point of view as well. We have some kind of a historical job performance trends. So in this particular widget, we can see that how a particular flow has performed over say last 1 month, and this can be used to detect some kind of anomaly if say for a particular date, if say the job runtime was abnormally high. So is this something that is expected, or is it something that needs some kind of developer intervention? So that is something that can be easily decoded from all of these dashboards. Basically, after comparing the Kingpin system with the older system, we can see we have reduced the operations and operational efforts by almost 70%. So earlier, a team of 10 engineers used to, kind of constantly used to monitor the flows and take care of reruns and all of that. But since Kingpin's inception, we have kind of narrowed down the on-call efforts to just 2 or 3 engineers across 10 different products. So, which is something that is definitely a step in the right direction. Integrations with Redash and Superset have drastically improved the system visibility, and we have now deeper insights on whatever jobs which are running in our system. We have integrated with Jira, we have integrated with Sparklins for actually, opening up more avenues for pipeline optimizations. So again, the gist is that no developer wants to spend too much time on the operation side of things, and with Kingpin, that is exactly what we have achieved so far, and we'll try to, improve further in this particular direction as well. So yeah, I think that's it for this session. Thank you for tuning in, and goodbye.